In our previous studies, we covered relevant knowledge about the forward rotation of motors. However, aside from the requirement for forward rotation functionality, achieving reverse rotation is equally crucial for our production and daily life. So, how can we achieve the reverse rotation of a motor? We typically describe clockwise rotation as a motor's forward rotation. In contrast, counterclockwise rotation is defined as the motor's reverse rotation. To achieve reverse rotation, we need to change the phase sequence of the three-phase currents supplied to the motor, using UVW/UWV as an example, or alter the sequence of the three sets of stator windings connection in the electronic circuit. This results in generating a counterclockwise composite rotating magnetic field when the windings are superimposed, leading the rotor to rotate counterclockwise and thus causing the motor to reverse. This principle can be seen in the diagram, which is exactly the reverse of the forward rotation. From the perspective of motor reverse rotation principles, the essence of switching between the states of forward and reverse rotation is changing the power supply sequence to any two phases of the motor's three-phase windings to switch the circuit from forward to reverse. Now, let's explore how to achieve this switching within electrical control. Firstly, we will introduce a relatively simple method using a reversing switch for toggling between the forward and reverse circuits. A reversing switch is a special type of control switch. As shown in its schematic diagram, the reversing switch has multiple switching positions. Using the reversing switch, you first set the switch to the forward position, which connects the motor to the forward circuit, resulting in forward rotation. To switch to reverse, you need to reset the switch, stop the motor, and then set the switch to the reverse position to enable reverse rotation. This is a straightforward and convenient method for switching, but it has drawbacks. Directly switching from forward to reverse while the motor is running forward can lead to significant reverse current that damages the motor windings. We can introduce an auxiliary circuit to prevent such large reverse currents from occurring in the circuit to avoid operational mistakes. Next, let's learn about the basic forward and reverse circuits for a three-phase asynchronous motor. In our previous exploration of the forward circuit of the electric motor, we often utilized a contactor to initiate its start within the circuit. Similarly, we employed another contactor simultaneously to achieve a reverse start, facilitating a transition in the circuit, referred to as a commutation circuit. This basic commutation circuit is achieved through two contactors. By connecting the control circuit of the motor to the forward and reverse circuits through the normally open contacts of two contactors in the auxiliary circuit, we can control the forward and reverse rotation of the motor using buttons. Let's take a look at the schematic diagram. KM1 controls the forward rotation contactor, while KM2 controls the reverse rotation contactor. In the main circuit from top to bottom, the low-voltage circuit breaker QS is the power switch for the entire circuit. The fuse FU1 provides short-circuit protection for the main circuit. KM1's normally open main contact and KM2's normally open main contact are included in the main circuit. Additionally, there's the thermal element FR of the thermal relay and the motor M. In the auxiliary circuit, there's the fuse FU2, normally closed contacts of the thermal relay FR, the stop button SB1, the forward start button SB2, and the reverse start button SB3. KM1 and KM2 are the coil and self-locking contacts of the forward and reverse control contactors. Having reviewed the schematic diagram, we can analyze the circuit states. Based on the circuit goals, it's clear that the circuit can have three states: stop, forward start, and reverse start. Let's take the example of transitioning from stop to forward start and then switching to reverse start for circuit analysis. First, let's consider the forward start of the circuit, with circuit breaker QS closing. Press the forward start button SB2 by hand, energizing the coil of contactor KM1. The motor in the circuit is connected to the power source and starts rotating forward. In the auxiliary circuit, the normally open contact of the forward direction self-locking closes, completing the action. The process for reverse rotation is similar, requiring pressing the reverse button after stopping the forward rotation. If another start button is pressed during operation, the coil of the corresponding contactor will be energized. This leads to both main contacts of the two contactors closing simultaneously in the main circuit, causing simultaneous short-circuiting of the forward and reverse circuits. To prevent this situation, we introduce the concept of interlocking. To ensure mutual restraint between two or more circuits, we prevent simultaneous energization action of circuits in the basic forward and reverse circuits. In the control of the forward and reverse circuits, a normally closed contact of another contactor is connected in series for each circuit. This arrangement ensures that the other circuit cannot be energized simultaneously during the operation of either the forward or reverse circuit. This relationship between the two contactors is called interlocking of contactors, and the normally closed contacts that achieve this interlocking function are referred to as interlocking contacts. As depicted in the schematic diagram, this set within the diagram represents the interlocking contacts. The principle is similar to the basic forward and reverse circuit, and we won't delve into extensive analysis. However, in the process of switching the circuit between forward and reverse, a stop segment is added, which increases the operational steps. So, is there a way to achieve a direct transition between forward and reverse while ensuring circuit safety? Next, let's delve into the circuit for the dual interlock of the forward and reverse motion of a three-phase asynchronous motor. The dual buttons that initiate forward and reverse motion are replaced with a composite button in the interlocking contactor circuit to facilitate a direct transition between forward and reverse while ensuring circuit safety. In the control of the forward and reverse circuits, a normally closed contact of another composite button is connected in series for each circuit. This constitutes the circuit for dual interlock of forward and reverse motion. Building upon the contactor interlocking circuit, we replace the two forward and reverse start buttons with composite buttons. In each forward and reverse control circuit, we connect the normally closed contact of the corresponding composite button. When you press the start button, it stops the action of the other circuit, releasing the interlock of that circuit's contactor. As a result, the circuit becomes energized. The key difference in the schematic diagram compared to the previous circuit is the replacement of the control buttons with composite buttons and connecting of the normally closed contacts of both buttons in series to achieve button interlocking. This circuit inherits the protection against short-circuiting due to the simultaneous activation of forward and reverse circuits from the previous circuit. Furthermore, it enhances the safety and reliability of the circuit. With button interlocking, the motor can easily toggle between forward and reverse rotation, significantly facilitating circuit operation. We have covered the four control circuits for three-phase asynchronous motors forward and reverse rotation. From easy to complex, this process represents the journey of problem identification and resolution in the context of learning. That concludes this lesson. Thank you, everyone.